Hi, I'm gonna go over the definition of an inner product space, and I wrote my notes by hand before recording instead of writing on the slides or as I go because it's gonna be time consuming. I'll slow down when I have a lot of information on the slides, but to start, I'm gonna go a little bit fast. Definition of an inner product space. As we could see now right here, we begin with a review of the dot product. As you can see, I'm not writing as I'm recording. I just want to go a little bit faster to save you some time. So what's a dot product? If we have two vectors, x and y, in r to the third, as you could see, the dot product of x and y can be defined in terms of the components of these vectors as x dot y will multiply x1 times y1, the first components. We multiply x2 by y2, x3 and y3, and add them up, as you could see in green at the bottom side. Now, the corresponding geometric vectors are using I, j, and k. So the first vector will be x1i plus x2j plus x3k, and same thing for the vector y. The geometric definition of the dot product is a little bit different, which is x dot y equals the magnitude of x multiplied by the magnitude of y and multiplied by cosine theta, which is the angle between the vectors x and y. So theta is the angle between the vectors x and y, as you could see, and we're going to see some applications and examples. If the two vectors are equal, so taking y equals x will give us the following. The magnitude of x being squared, which is x dot x, will equal x1 square plus x2 square plus x3 square. So that the length of the geometric vector is given in terms of the dot product by the following. This would be the magnitude of the magnitude of the vector x will be the square root of x squared plus x1 squared plus x2 squared plus x3 squared. The angle between any two non-zero vectors x and y is, after of course you solve for theta, taking cosine inverse to both sides, will be the dot product divided by the magnitude of x and y. For any non-zero vectors x and y, since x dot y equals the magnitude of x times the magnitude of y times cosine theta, we get the following. If the dot product equals 0, we say that x and y are orthogonal or perpendicular. Let's see why. Well, of course, x cannot equal to 0, because we just said for any non-zero vectors x and y. Also, y cannot equal to 0, so they're both are not equal to 0. So the 0 should be coming from cosine theta. So if we have the following, as I said, it has to be coming from cosine theta. If cosine theta equals 0, then theta equals 90, or pi over 2, of course. We will use the standard inner product in place of the dot product. So from now on, when we say inner product, we kind of refer to what we know for the dot product. Inner product is defined different ways depending on your vectors. That's one reason we don't use the word dot product. Dot product is useful when you have x1, x2, and y1, y2. Also, we will use the norm in place of the length or magnitude. So two things we're going to be using, which is inner product and norm as like dot product and magnitude. Definition. So we have two vectors x and y in R to the n. We define the standard inner product in R to the n. In short, we write it this way, kind of like the symbols less than and greater than with x and y inside by the following. That's just kind of like close to what we used to call dot product. We just multiply and add the components. The norm of x is, which is the length, the way we call it, is the square root of the dot product between x and itself. And now we view the standard inner product in R to the n as a mapping that associates with any two vectors x and y in R to the n the real number. So you have two vectors, you apply the dot product or the inner product, and you get an answer which is a scalar. This is called a mapping. So when you add the products of x1, y1 and x2, y2, that's going to be our output. This mapping has the following four properties. For all x, y, and z in R to the n, and all real numbers k as scalars. Number one, the dot product between any vector and itself should be greater than or equal to 0. And it will be 0 if and only if x equals 0. So the vector itself is 0. Number two, the dot product between y and x will be the same as x and y. Number three, if you have a scalar k multiplied by x, then you do the dot product with y would be the same as the dot product between, or the inner product, I keep saying dot product, the inner product between x and y multiplied by the scalar after. Number four, so if you have a sum of x and y vectors with the dot product or inner product to z, that will be kind of like, if you want to call it distributive, dot product, inner product between x and z added to the inner product between y and z. Definition. Let V be a real vector space, a mapping that associates with each pair of vectors u and v in V a real number, which is an inner product u and v, is called an inner product in V, provided it satisfies the following properties. For all u, v, and w in V and all real numbers k, the dot product or the inner product between V and itself will be greater than or equal to 0, and it will be 0 if and only if V is 0. Inner product between V and U is the same thing as inner product of U and V. Scalar k multiplied by U, inner product with V would be the same thing as U, V, inner product, then after that multiplied by the scalar k. Number 4 is similar to last time. The sum of u of v inner product with w will be the sum of the inner products u, w, and u, v. The norm of v is in terms of an inner product by the following. This is called the norm, and similar to what we had before, a real vector space together with an inner product defined in it is called a real inner product space. One of the fundamental inner products arises in the vector space C power 0, if you want to call it that way, from A to B, of all real valued functions that are continuous on the interval from A to B. So if you see this notation, that means real valued functions that are continuous on the interval A to B. In this vector space, we define the mapping between two functions f and g by the following. It's the integration from A to B of the product of the functions f and g with respect to x for all functions f and g in C0 AB. If f is in C0 AB, then the product or the inner product of f and itself will be the integration of f by itself, f times f, or f to the second square from A to B. Example: determine the inner product of the following functions in C0, 0, 1. We have 8x, we have x squared minus 1. Also find the magnitude or the norm of those two functions. Solution. First, we do the inner product between f and g, so we have to do the integration of the product of f and g from 0 to 1. We just multiply 8x times x squared minus 1, and we just apply normal integration, apply the limits 0 and 1, and we get negative 2. The magnitude of f as a vector f, which is a function, will be the square root of the integration from 0 to 1 f squared, but since f is 8x, f squared will be 64x squared, and that will end up 8 over square root of 3. Magnitude of g, same idea, take x squared minus 1, square it, apply normal integration, and you should end up with got the integration inside, so let's add it right here from 0 to 1. Square root of 8 over 15. Another example. Determine the angle between the functions f of x equals sine 2x and f2 of x equals cosine 2x on the interval from negative pi to pi. Solution. So the integration from negative pi to pi of those two functions being applied, f1 times f2, will be sine 2x cosine 2x. To do that, we need to use trig identities, and now we have the following. Since sine 2x equals 2 sine x cosine x, we have sine 4x equal 2 sine 2x cosine 2x. So the right hand side is sine 2x cosine 2x will be replaced with half sine 4x. So now we have half sine 4x to be integrated. We let u equals 4x, u substitution, and we'll move on from there. U equals 4x, then du dx equals 4, or du over 4 equals dx. Integration becomes 1 over 8 of negative cosine 4x from negative pi to pi equals 0, since we want the product to be, the inner product to be 0. The angle between the two vectors should satisfy cosine theta equals 0. Of course, when you apply the inverse of cosine, your angle has to be restricted between 0 and pi. Therefore, theta equals pi over 2. We say that the functions are orthogonal on the interval from negative pi to pi. Now let's move on to complex inner products, vectors in Cn. Complex inner products, vectors in Cn. The components of vectors in Cn are complex numbers. Applying the r to the second or r2 inner product, for example, the vector v equals 1 minus I, 1 plus I is not a zero vector. But if you do the magnitude or the norm, applying the math, you get 0. That's a problem. Which means that a non-zero vector would have a 0 length. To fix this, we must define an inner product in Cn carefully. We take advantage of the complex conjugate. Definition. If u equals u1, u2 up to un, and v equals v1, v2 up to vn in Cn, complex numbers, we define the standard inner product in Cn by the following. The inner product between u and v will be u1 v1 conjugate plus u2 v2 conjugate plus all the way to un vn conjugate. The norm of v is defined by the real number. Once we apply the norm for the same vector, we're gonna also apply the conjugate because we're doing products of components. So here's an example. U equals 5 minus I minus 3I, 6 plus 2I, and V equals 2I, 1 minus 1 minus 4I in C3. We need to find the product or the inner and the norms of U and V. Solution. We just apply, as you could see, the definition that we created. So if you multiply the first component of U, which is 5 minus I, the first component of V is a 3, but the conjugate of 3 is still 3. We take the second component, which is from the first vector minus 3i, times the second component conjugate, which is 2i conjugate, and that's going to change to minus 2i. Third component, 6 plus 2i, times the conjugate of minus 1 minus 4i, will change to minus 1 plus 4i. Doing the math, we end up with minus 5 plus 19i. Now we apply the same thing when you do the norm of u. Since when I'm applying the components of u, 5 minus I times 5 minus I, we need to keep in mind the conjugate from the definition. As you could see, we have the 5 minus I conjugate, the minus 3I conjugate, and 6 plus 2I conjugate. Doing the math, we end up with 5 square root of 3. As you can see, I'm writing this before, because if I keep writing all these examples and all these steps, it's gonna be a lengthy video. Same thing we apply for the magnitude v, and this time I skipped a step. Instead of writing the conjugates on top like those red bars on top, I just did it and I skipped that step. Note, if z equals a plus ib, then z conjugate is a minus ib, and z magnitude squared will be z times z conjugate, which ends up a squared plus b squared, just to remind you. Now we use the properties satisfied by the standard inner product in Cn to define an inner product in an arbitrary real or complex vector space. So we go back to the definition. We have V real or complex, and we have vectors in V like U and V. We define inner product, or we have a scalar that we use, which is K. The symbols less than U and V greater than will be called inner product, provided it satisfies the following properties. For all U, V, and W in V, and all scalars K, we have the product, or the inner product V will be greater than or equal to 0, and it will equal 0 if and only if V equals 0. Now what's interesting is number 2 here, so I'm not gonna read 3 and 4. Number 2, as you could see, we do V U inner product will be the conjugate of UV inner product. We can switch them, VU and UV. The norm of V is defined in terms of the inner product. Example on property number 2. If U equals 2 plus I, 3 plus I, and V equals 1 plus 2I, 2 plus 5I, in C2, we have the following. Looking at the left, UV equals, all this right here is displayed for you, 2 plus I times the conjugate of 1 plus 2I, and so on. So I take the first components from U and I take the conjugates of the second components from V. End up 15 minus 16I. Notice if you do V plus 2I, sorry, V and U right here, that's gonna end up 15 plus 16I. Where earlier we had UV, which is the other way around, gave me 15 minus 16I. Well, that says that they're not the same. They're conjugates. And that kind of explains property number 2. What's interesting is, as you could see from here, in case V is a real vector space, the complex conjugate are unnecessary. In that case, UV equals conjugate of UV is just VU equals UV. just like the earlier definition real vector space. So this covers, or the last page covers both real or complex, as you can see, real or complex. All right, back to this, and now I think we are done. Hopefully you like this video, and thanks for watching. This is my first video doing it this way. I hope that it was helpful. I tried to cover enough, and I had to make it this way instead of writing all my notes as I am recording, to save you time watching. Let me know if you do like it and comment below, and maybe consider subscribing. Also, hit the like button if you do like it. This will encourage me to do more. If you like this video and you want to be notified when new ones comes up, hit the bell icon. Until next time, peace. JaberTime. As you can see, this is my first video, so rewriting these notes or writing these notes before the video takes a lot of time, and I'm trying to save time because a good video, I believe, has to be as short as possible, to the point. So thank you for watching, and we'll see you next time. Thank you.